Friends, after studying the bivariate regression or simple regression, we have seen that there may not be a single variable which is causing the variation in the dependent variable. There could be several explanatory variables which are impacting the dependent variable. This could be clear from the model fit of binary regression giving us a very low value of coefficient of determination. So, one of the reasons for that could be that we have not taken into account other factors which are responsible for creating the variation in the dependent variable. In the sense that instead of binary regression or simple regression, we should consider the multiple regression. So, this is the topic of today's lecture, multiple regression analysis. The agenda for this presentation is as follows. What is multiple regression analysis and when should one use it? Types of regression models, understanding various aspects of multiple regression analysis, coefficient of determination R square, and an example for multiple linear regression. So, just I was introducing to you that when should we use multiple regression analysis? When we analyze the relationship between two variables, one dependent and other independent, and we come to see that that relation is not helping us enough in understanding the variation in the dependent variable. So, one of the reasons could be that there are more explanatory variables which we have not taken into consideration. So, in multiple regression analysis, we will now analyze the relationship between more than two variables which could be linear or non-linear. Again, we are not going to go into the non-linear situation. We will consider multiple linear regression analysis. Regression analysis can be used to identify the explanatory variables that can most effectively influence or control the value of the outcome variable. The objective of multiple regression analysis is also the same as that of simple regression. We would like to estimate, predict or forecast the dependent variable given the values of the independent variables. So, we have seen this tree diagram in our previous regression session. That time I had said that we are considering the simple linear regression. Now we are talking about the multiple linear regression, and that too only the linear part, where there are two or more explanatory variables. Actually, there could be more than one dependent variables also. So, those kind of models are also there in statistics, where you have n number of dependent variables and some m number of independent variables. Then the things and the analysis becomes more complicated. Right now, in multiple linear regression, we consider that there is a single dependent variable and say k number of independent variables. So, in short, multiple regression is the extension of simple linear regression model. It includes one dependent variable and more than one independent variable, and outcome variable is affected by these independent variables. So, that is the model that we are talking about. We are into the linear setup. So, if you remember that we had started with y equal to alpha plus beta x for binary regression. Now, if there are k such predictors, then you will have to start with the equation as y equal to some constant plus coefficient times x1 plus another coefficient times x2, and likewise coefficient times xk. So assuming that there are k such predictors or explanatory variables. So like the estimate b of beta in the simple linear model, we want to estimate now these coefficients by using our data. So we assume that we have the data on all these variables x1, x2, xk as well as y. For example, if we are talking about the systolic blood pressure of a patient, then it may not necessarily depend upon only the age of the patient but also on the weight of the patient. So in that case, x1 can be considered as age, x2 as weight, and then you model the systolic blood pressure by using b0 plus b1 x1 plus b2 x2. Again, if you think that there should be some other factor taken into consideration, say hemoglobin, then you will add that variable and again fit the same model. If you remember, we have talked about the method of least squares principle. So the same principle is applied in the multiple linear regression setup also, and these parameters betas are estimated. In case of simple linear regression, it was a straight line. Here one should imagine a plane, k dimensional plane, and then you are talking about the distances of the data points from that plane, and you minimize those distances, etc., using the calculus method, and you estimate the parameters. So beta i's are the same as in the simple linear regression case. Beta I represents the expected increase in response y for a 1 unit increase in the variable xi when all other xi's are held constant. So if you are talking about the beta 2, suppose, then that means you are talking about the regression coefficient of y on x2 given that the other variables x1 and x3 are constant. So that's basically they are known as the partial regression coefficients, but here we will call them as regression coefficients of y on x2. See, so the ideas and concepts are similar. These beta i's are estimated by using the least squares method. Let us have a look at some situation, data, and an example run in SAS. Symptomatic recovery in pediatric dehydration. A study was conducted to determine the degree of recovery that takes place 90 minutes following treatment of 36 children diagnosed at the clinic with moderate to severe dehydration. Upon diagnosis and study entry, patients were treated with an electrolytic solution at various dose levels in a frozen flavored ice popsicle. The degree of dehydration was determined by using a subjective scale based on physical examination and parental input. These scores were converted to 0 to 100 point scale representing the percent of recovery. So the response endpoint is the percent of recovery. What are you recording? You are recording the child's age and weight also. So they become the independent variable. Is recovery related to electrolyte dose based on the data? So patient number, this is our response endpoint y. Dose is obviously one of the factors, age and weight. So here we want to fit the multiple regression of y on x1, x2 and x3. x1, x2, x3 become the independent variables. Now the term independent variables is actually a misnomer, since x1, x2, x3 they are not independent in statistical sense. They are actually explanatory variables. Why I am saying that? Because they could be related. For example, age and weight, there is a correlation between age and weight. So when we say That's these three are independent variables. They are not independent in the statistical sense. They are independent from the regression analysis sense. Anyway, okay, this is the data, and you have input that data. You are asking SAS to print data also, and here you observe that you are using proc reg. You are asking the proc to give the correlation coefficients matrix also. Model Y equal to dose, age, weight. Model Y equal to dose. Model Y equal to dose and age. Model Y equal to dose and weight. Now what are all these? The proc reg allows you to specify multiple regression models. So you are asking the proc reg to first consider the model Y, which is dependent on dose, age and weight. All the three variables considered. Next, you are asking it to consider only Y equal to dose. That means it is our simple regression. Here, Y dependent on dose and age. You are not considering weight. And here, Y as dose and weight. Obviously, dose is everywhere present because that is the factor under study. How is it causing the percent recovery? That's very important. So you are not removing dose, but you are trying all other combinations of the explanatory variables. Once you run this SAS program, it gives you the correlation coefficient matrix. I suppose we have seen this kind of matrix earlier also. Since there are 4 variables, it's a 4 by 4 correlation matrix. So dose with dose, the correlation coefficient is 1. So correlation coefficient between the variable and the variable itself is always 1, and you get all the diagonal entries 1. Between dose and age, this is the correlation coefficient. Between dose and weight is the correlation coefficient, and so on and so forth. Between Y and age, the correlation coefficient is negative. So as age increases, you seem to recover less from that particular disease, dehydration. Similarly, the weight and Y, they are also negatively correlated. So this initial idea that you get. Now the first model is, its output is given here. The model sums of squares, error sums of squares and the total sums of squares. The model sums of squares 2667.66870. You compute some mean sums of squares and F value. This is known as analysis of variance table. We will see the entries and its description in the analysis of variance table when we learn the topic of ANOVA, that is analysis of variance. But here what it tries to tell you is that when you are using the model 1, that is the first model, which was that first model? That first model was with all the variables, all the independent variables considered. Then the F test statistic value is 9.03 and the p value, this is the p value, which is 0.0002, which is far less than 0.05. We will interpret this value after some time. Root mean sums of squares, dependent mean, coefficient variation, etc. R square. These are the things which of our interest. R square is the coefficient of determination that gives us an idea about the strength of the model, how good the model fit is. And then this is adjusted R square. So some modification of the R square. So henceforth we will be considering adjusted R square in place of R square for comparison purposes among different models. The answer to that I will tell you once we complete this interpretation. So the first model, if you remember, the first model in the SAS program was having intercept, dose, age and weight. So these three variables and the intercept. So B0 plus B1 x1 plus B2 x2 plus B3 x3. And then what are these B1 x1 etc.? So this first value is the value of intercept. Then this is the second value is the coefficient of dose. Then the third value is the coefficient of age. Fourth value is the coefficient of weight. So you can literally write an equation as y equal to this intercept plus 6.16 times dose plus 0.276 point age minus 0.42 times weight. That's the model that we are talking about. And this T statistic for establishing the significance and non-significance of the respective variables. So here you get it as 0.0016. So dose is very significant. I am comparing it with 0.05. Since it is far less than 0.05, dose is very significant. Obviously it has to be for the response variable. Age, the p-value is 0.9043 greater than 0.05. So it is not that significant or not at all significant. Weight is 0.10, so it is also not that significant. Let us proceed. Then it gives some other statistical quantities, collinearity diagnostics, eigenvalues etc., which are currently out of the scope of this lecture. Now the second model that you tried was having two variables, dose and age. So for that, if you consider dose weight, that means you are not considering weight. If you don't consider weight, then what is the situation? Your F value is 11.51. This P value is also very less. So this model also fits good, but the R square, adjusted R square is 0.3751, which is lesser than the previous value. When you consider another model 4, which is having dose and weight, then also you can get the similar such quantities and you can compare the R square for that, T value, this is the P value, and this is that model where you are considering dose and weight, and the adjusted R square comes out to be equal to 0.4254. So the prediction model can be written from the parameter estimates as follows. Here we have selected the model which we have fitted with all the variables because it gave us the highest adjusted R square, and that was y equal to 85.48 plus this is regression coefficient for dose multiplied by that dose plus 0.28 age minus 0.54 times weight. A printout of the dataset is first obtained using proc print. The CORR option in the proc reg requires the inclusion of the correlation coefficients. We have seen that matrix. Note that age and weight are highly correlated. The correlation coefficient is 0.9367 and that the degree of recovery at 90 minutes after treatment is positively correlated with dose and negatively correlated with age and weight. And the F value was 9.03 for the model statement is a global test of the hypothesis with the p value very close to 0.0002. So indicates that the response is linearly related to at least one of the independent variables. That is the language in which statisticians talk, but mainly that gives you whether the model fit is good or not, and the predictability of the model is provided by the value of R square, that is coefficient of determination. So it indicates that about 46% of the variability of the measured responses can be accounted for by the explanatory variables dose level, age and weight. So, this is the interpretation of the output. As we have observed that multiple model statements were used in PROC-REG. PROC-REG is a general regression procedure available in SAS. You can use other regression procedures like PROC-GLM, PROC-CATMOD, PROC-GenMod depending upon the typical situations that you are in. So, if you go to the respective help of those procedures, you will come to know that what are the differences between these different procs. But essentially, the idea behind all these procedures is the same. The second model statement requires a simple linear regression, etc. So, this is again the explanation of what has been done in the code. So, there are so many models we have tried and we have seen that the coefficient of determination of R square 41.1 was obtained by using dose level and age, and then R square of 45.8 is found with dose level and weight. These results indicate that if age or weight is used in the model, including the other does not help much. So, the final model used is model 4 because it has the highest R square. With this model, weight is highly significantly explanatory variable. So, this is the way in which one can interpret the SAS procedure output. Now, the only thing remaining which I wanted to tell you is in place of coefficient of determination R square, we use the adjusted coefficient of determination, that is adjusted R square. Now, what happens in case of multiple regression, you may go on taking data on number of variables. Here we have seen an example where we have x1, x2, x3 and the dependent variable. Suppose you think tomorrow that I want to have some other variable also available in the data. So, you take the observation on say some x4. Then what will happen to that R square? R square will always increase. So, as you go on adding the number of explanatory variables, the R square will go on increasing. So, what will then it suggest? It will then suggest that the more number of variables gives you better fit. But actually that may not be the case, because that may not be improving on the predictability of the model. So, in order to remove this effect of getting that R square increased every time by increasing the number of variables, there is some adjustment made to that R square, and that adjustment is called as adjusted R square. So, once you do that you compute that adjusted coefficient of determination, then you need not worry about that unnecessary increase in the value of coefficient of determination. With adjusted R square, even if you have 5 variables, 6 variables, 8 variables, it will give you the correct idea about the credibility of the model. So, always compare the adjusted R square among different models and then decide which model you will use. So, that is what about the multiple regression analysis that we have talked about. We have talked about the multiple regression analysis, when should one use it, different types, understanding various aspects of multiple regression analysis, then the coefficient of determination R square and multiple linear regression example. I would say that whichever data you have, you can just use them and fit this PROC-REG or PROC-GenMod or PROC-GLM, see this as output, try to interpret the output and try to interpret the output from the context of the study also, in order to get the better and better insight of the data.